So yes, Phil says, I'm going to talk to you about C++ compiler tidbits. You probably know or seen my website, and this may explain why we're going to be talking about how cool compilers are. So let's just, oh, if I can click in the right place. Focus. Hi, everybody. So I'm Matt Godbolt. I'm accidentally a verb. I created this website, and then for reasons unknown to me, people wanted to call it Godbolt instead of Compiler Explorer, which is its true and proper name. And I've sort of become a verb. And we're going to talk a little bit about that, and moreover, why you might want to use the site, why the site's cool, and moreover, why the site came into being and how cool compilers are. So compilers are absolutely amazing. They're fantastic. They're an amazing feat of engineering. And I don't think we spend enough time thinking about what the compiler is doing for us. So what is a compiler to you? Certainly when I started my career, a compiler to me was something which took some code that I'd written and turned it into the game that I was working on, right? It was just a means to an end. And then I started getting more and more interested in the language itself. And I started learning things, you know, like template metaprogramming and things like that. And so then quickly the compiler became something which took the code that I'd written that clearly worked and turned it into hundreds of thousands of lines of error message. That is not really what I'm going to be talking about today. We're not going to do too much talking about unusual C++ corners. What we're going to be talking about is the kind of code that you write that looks pretty straightforward and simple. This example on the left-hand side here is fairly standard. You could write it using accumulate or any number of ways. And the beautiful poetic code that the compiler generates, the assembly code that the compiler generates on your behalf. And I do mean poetic. It's beautiful. It is. I want you to come away from this talk thinking that assembly code is like Shakespearean poetry. It's very hard to write yourself. You don't necessarily have to understand every last detail of it, but you can get the gist of it and appreciate how well it has been written. So yeah, I did say assembly. There's going to be quite a lot of assembly in this. And because of where I work and the experiences that I have, this is all going to be x86 64 assembly. So modern Intel assembly. Obviously, there are many other chips out there, most notably the ARM processor that's inside pretty much every cell phone going and almost every device around your house. It's fair to say that there is a big difference between the different architectures, the ARM and the assembly, the ARM and the x86, and the very specific things that I'm going to show you about some of the more unusual x86 things don't necessarily go across to ARM, but broadly speaking, the kinds of tricks the compiler can pull are similar for each architecture. They just have their own nuances. So forgive me if you don't really know x86. By the end of this, you'll know enough to get by. And often, you know, when I show like a junior programmer and I go to the disassembly view straight away at something, they look at me like, what is this? What is this going on here? Why are you showing me this? I wanted you to not have that fearful reaction. So in general, each assembly instruction is a very primitive operation inside the computer. It has an opcode name and it has 0 to 3 operands. So think of it like a function call with some number of arguments, and the arguments are sometimes read-write so that you can actually get results out of them. So here's some example x86 instructions. So a single ret is a return instruction. That means that we finished doing this line of work and we want to go back to whatever we were doing before. That takes no parameters. Something like inc racks, increments racks. So that's like racks plus plus, right? We'll talk about what racks and all the other strange named things are in a couple of slides' time. So that's got a one argument, and the argument is both a source and a destination. You know, when you're doing racks plus plus, you're reading and writing racks. Mov edx, 1, 2, 3, 4. Here I'm using 2 operands. The 1, 2, 3, 4 is one of the operands, and edx is another strange name thing. And what it means is move the value 1, 2, 3, 4 into edx. And of course, it's not move. It means copy. Copy the value 1, 2, 3, 4 into edx. It doesn't wipe out 1, 2, 3, 4 from the world. Sort of now we're into the sort of peculiarity of x86. So an add instruction. This is where we're doing RSI plus equals RDI. For many of the instructions that the x86 has, unfortunately, you're cursed to do these plus equals or minus equals or times equals operations. There are only 2 operand versions for this. So there isn't like a x equals y plus z version, you have to do RSI plus equals RDI. So you'll see the compiler has to do some gymnastics to kind of keep that keep things in the right place. But add is a mutating operation. It says RSI plus equals to whatever RDI is. Some of the newer instructions, like this VP add, which is a vectorized parallel add instruction, when they extended the instruction set, they actually allowed it to take 3 parameters. So this one can actually do YMM equals YMM2 plus YMM0. So there are some newer instructions that do have 3 operands, but most are limited to 1 or 2. Okay. Now, what instructions do we have? I just showed you a few of them there. I ran a random sample on my machine. I wrote a little program to stop the globally stop the program counter and say, what instruction are you executing right now? And I was running Compiler Explorer and a web browser and all the bits and pieces. And I took the top 20 instructions, and this is what they are. And they aren't that complicated, right? So, you know, if you know these 20, you pretty much know a good amount of the CPU instructions you'll ever encounter. Let's just go through them in groups. The first set of instructions that appeared are these move instructions, and they are basically copying data around. They can move data from registers to registers. They can move data from registers to memory, from memory to registers. They can do 0 extending and sign extending. You'll see those when you're dealing with smaller values, you know, like your unsigned in 16T that you're extending into a big 64-bit value. LEA is a special case, and we'll get to LEA in a bit, but it sort of broadly fits in with the move instructions. We have some control flow instructions. Call goes to a subroutine or a function. Ret comes back from it. Jump is an unconditional jump to somewhere else in the program, like a goto, really. You know, although you're not supposed to write gotos, the compiler writes them all the time for you. We've got push and pop to manipulate a stack. We can compare and test, which are similar enough that you don't need to worry about the differences. And then you can jump if equal or jump if not equal based on what that comparison was. And obviously there are jump if greater than, jump if less than, jump if above, all the different kind of combinations of things that you might need to do for your comparisons. But in this sample of the top 20, only jump if equal and jump if not equal came up. Then finally, we get onto some instructions that are actually doing something with data as opposed to just loading it and storing it and jumping around. We can AND or exclusive OR, add and subtract, and then shift left, shift right, and SAR is shift arithmetic right. So to a first approximation, all the maths that we ever do is adding and subtracting, ANDing, exclusive ORing, which seems very surprising. Oh, and shifting up and down, which is, you know, multiplying by a power of 2 or dividing by a power of 2, depending on how you look at it. So it's surprising to many people to see that exclusive OR is in that list, and we'll see why that is in a little bit. But the rest of them sort of vaguely make sense. I guess AND is surprising too. But those are the top 20 instructions on my computer list when I ran this sample. And of course, there are many, many more. And in particular, for x86, there are very many more. There are like thousands upon thousands of instructions. But they're very niche, and oftentimes you only need to look them up when you see them for the first time. So I keep talking about these operands and like kind of these raxes and things. What are these operands? What can they be? So the first thing that an operand could be is a register, which is that rax or EDX or any of the other strange names that you've seen. And we've got a slide for those in a second. It could also be a constant. We've also seen that. We saw that in the MOV ECX, 1234. It was just a constant, and that's just stored in the instruction itself. And it's a value that will be put into the register or added to a register. And then this is now quite a peculiar x86 thing, and that is one of the operands can be a memory access. In simpler RISC-like processors like ARM, there are dedicated instructions to load and store from memory. In x86, it's just like an operand or like a register or a constant. You can just refer to memory as you go. And moreover, you don't just have to say, read the bytes over here and add them to me, please. You can say, read the bytes from over here through a pointer, a register. You can say, read the bytes that are this register plus some constant offset. Or you can say, read the bytes that are at this register plus some constant offset plus some other register multiplied by 1, 2, 4, or 8, which is really complicated, right? That's an operand. That's just part of the instruction. It's not the whole instruction. That means that you can write an instruction that looks like this: add EAX, comma, dword putter, RDI plus 12 plus RSI times 4. That is one instruction even though it corresponds to the C++ code, or C code, I suppose, that I've written on the line below, which is, plus equals int star of this complicated expression. This is because the legacy of the Intel sort of history, it was often very useful to be able to access elements in an array. And of course, most elements in arrays of primitives are either 1 or 2 or 4 or 8 bytes long. And so you can refer to the ith register, sorry, the ith element in an array by saying base of the array plus the offset times 1 or 2 or 4 or 8. And that's really, really handy. But it has other uses, as we'll see in a minute. So let's talk about those registers. I keep waving my hands about them. They're essentially the only things you can operate on in terms of adds and subtracts and things. You can do some things with memory, but mostly this is where the values are going to be stored that you're actually operating on at the moment. Think of them as like global variables that you have to share with your whole program. So you have to push and pop them and whatnot. And then when you call a function, or when a function returns to you, there's a kind of agreement between the caller and the callee about which registers need to be kept the same, which registers can be overwritten without any problems, and which registers hold the information of the parameters that I'm passing into a function, or the parameter that's coming back out of a function if it returns a value. And so in this Linux x86-64 setup that we have here, the RAX register, the A register in old money, is the return value. If you call a function and it returns an integer, the value will be in the A register. If you're passing parameters in, you're expected to put them, the first parameter in RDI, the second parameter in RSI, the third one in RDX, and then there's a list of where the rest of them go, which I haven't bothered putting here, because if you're passing more than 3 parameters to a function, you want to have a think about that. There are a whole bunch of other weirdly named registers, RBX, RCX, RBP, and so on. And then when AMD extended the register set, when they went from 32-bit to 64-bit, and yes, it was AMD rather than Intel that designed this extension, they decided to add 8 more registers, but gave them sensible names. So those registers are R8 through R15. Excuse me, I've got a bit of a frog in my throat. There are also some extended multimedia registers that hold very wide values that can be operated on in parallel. Those are called XMM 0 through 15, or YMM for the slightly wider ones on newer CPUs. And on the latest AVX 512 CPUs, these registers can be 512 bits wide, and they're called ZMM, and so on. And some K registers as well. We don't need to worry about those for what we're looking at today. So broadly, oh, I forgot about this slide, apologies. The other thing about a register is that it has different names depending on how many bits wide it is. So this all is the same register. Think of this as the A register, the register called A. But when you say racks, you're referring to all 64 bits of the register. When you say EAX, you're only referring to the bottom 32 bits of the register. AX is the bottom 16 bits, and AL is the bottom 8 bits. And so I can pass a value, if I'm only using 32 bits, I can pass a value using EAX. And if I add to EAX, then only the bottom 32 bits are affected. The top 32 are, in this case, are zeroed. So depending on what size operand you need to work on, you'll use a different name for the same register. But it is possible to write a value into racks, all 64 bits, and then just read out the bottom 32 bits by referring to EAX. And the compiler will occasionally pull these tricks on your behalf. Okay. That is my whistle-stop tour of assembly, and I'm hoping that you followed enough with that. Certainly when we go over some of the examples, I'm hoping that it will become more clear as I sort of do a line-by-line sort of walkthrough. And again, the real critical thing here is that I wouldn't expect anyone, myself included, to be able to sit down and understand exactly what's going on every single time. Getting the gist of it is important enough to be able to say, hey, that loads. Oh, that didn't load the memory. Oh, it just returned the value. Those are the kinds of things that I think are important to be able to see just by looking at the assembly. But mainly when we're looking at assembly, we're interested in performance. And although I'm going to show you a ton of Compiler Explorer stuff in a minute, the main thing to note about performance is that you absolutely, absolutely have to measure it. There are a number of really good ways of measuring performance. It's difficult to do it well, but Google Benchmark, some of these other things that I've got listed down here, and if you want to do a quick online check, quickbench.com are a great places to go and test out the actual performance of your code. It's really, really important to remember that just because something compiles to fewer instructions, it doesn't necessarily mean it goes faster. There are there's subtle interplays between instructions. Not all instructions take the same amount of time. Things like memory bandwidth are important too, and a multiply is more expensive than an add, and things like that. So we'll see some of those as we go through, but always more measure. So now on to the actual tidbits. Okay, we've spent probably too long explaining how to interpret these results, and let's talk about the kind of maths tricks that the compiler can do for you. So I'm going to go straight into Compiler Explorer and start with this very boring test piece of code, which is just going to show you roughly how to read the code in Compiler Explorer. So I'm going to load that up and hopefully it works. Come on, yay. That seems to be coming out readable enough on the stream. I'm looking over on my left-hand side here. So here we're taking two inputs and returning the subtracted value of those. So we're doing x minus y. And so on the right-hand side, you can see the code that's been generated by the compiler. I'm using an old version of GCC just because it fits in with my slides and things haven't moved around, but most GCCs will generate the same code for the kinds of examples that I'm showing you today. You'll see that I've got -02 on, which is not the highest level of optimization. I'll turn it on to 03 in some of the versions of the code, but mostly it generates a lot more code and doesn't necessarily show clear results. I'm also targeting the Haswell architecture, which is a relatively old x86 architecture, but it does allow it to use most of the new instructions. And if you can, when you're building your code, try and target the minimum CPU you know that you can run on it. It will help the compiler generate the right kind of instructions. So with all those caveats in the bag, we can see that what's happened is the test function here is assuming that the two parameters x and y are in EDI and ESI. And so we know that the x value is the first parameter that goes into EDI. And the first thing the compiler has to do is copy it to EAX. Why does it need to copy it to EAX? That seems weird, right? Well, because the only subtraction that we have is a minus equals, and we need the result to go in the EAX. Remember, the person who's calling us is expecting us to fill in the result of test, this x minus y, in the EAX register or the RAX register. In this instance, we're returning an int, which is 32-bit, so it's using EAX rather than the 64-bit RAX. So the compiler says, return value equals x with mov ex edi, and then it says return value minus equals y, and return, and we're done. So it's more complicated than you might imagine, but that's all the steps that the compiler has done to generate an x minus y. Now, if we were interactive and there were enough people around, I would ask people what would happen if I turned this minus into a plus, which is a very unfair question to ask because I know I wouldn't really be asking it unless it was surprising, right? So naively, if I was being asked that question, I would say, well, then it would just become add EAX, ESI, surely. And so let's find out. I'm going to change a minus to a plus. And now suddenly we've lost the whole instruction. We no longer have an add, and we don't even have that mov. We've got this LEA instruction, which I alluded to earlier and said I'd talk more about. So what the LEA instruction does is it's supposed to be used for memory operations. It is the load effective address instruction. And it says, treat the operand on the right, that is this block over here, as if I was going to read from memory at that location. And you remember, when we read from memory, we get to do a register plus a constant, plus another register multiplied by 1, 2, 4, or 8. But instead of reading from that address, I just want you to return me the address that you would have read from. So get me the address of RDI plus RSI. And just because of the way the instructions are encoded, that means I get to put two operands on the right-hand side as memory operands. Oops, excuse me, I'm banging my microphone here. And then I get to put the result in any register I want, because that's just how LEA works. And so the compiler is able to save that move into EAX and followed by an add by using this LEA instruction instead. It gives it essentially a result equals x plus y as a single instruction. And that's super cool, right? We don't need to know that it's doing that behind the scenes. It just does it. We saved ourselves a whole instruction. Even cooler is that if we start doing things like return x times, oh, I haven't got my keyboard far enough back, y times 4, the compiler is able to continue to use that LEA instruction, which again is designed to access memory. This is supposed to be used for, like, there's an array at RDI and I'm accessing the RSI integer in it. But adding, we don't care. We're not going to read from that address. It's just a number that we're adding together. So the compiler is able to do these clever things where it is doing these things on our behalf. Even more interestingly is we can start seeing how smart the compiler can be. So I'm going to change this test from being a multiply by 4 plus y, just to multiply by 4. And so here it's still able to use that LEA. It just uses a constant of 0 plus RDI times 4. And obviously if I do times 8, we get the same. But surely, if I put like 9 in here, it's going to fall over because we haven't got a times 9. But the compiler can build a times 9 out of a 1 plus, sorry, as in like x plus x times 8. And then, it can do the same with 7. It can just say, generate me times 8 and then minus 1 to get it back to being a 7 times. And all these other clever ways, the compiler basically, any kind of arithmetic you can do, the compiler will find a really smart way to build it out of these primitive, very fast instructions. An actual multiply instruction takes multiple cycles, like it takes a number of cycles, whereas these LEAs are very fast and they're designed because every memory access needs to do this kind of calculation, so they're quick. But eventually the compiler gives up, 6, no, that's cool, 7, we did that one, 13, yeah, all right, let's just pick a really big number, 65599. So eventually I'm going to give it a big enough number that the compiler says, okay, we're done here, I don't know anymore. I'm not going to build this out of shifts and adds and things. I'm just going to use the multiply instruction. And because we're in the Haswell here, it knows that there is actually a 3 operand multiply. So this is doing EAX equals EDI times 65599. And so unfortunately, it gives up eventually, right? Now, when I was in the games industry, we used to build our own multiplies out of shifts and adds because we'd never trust the compilers, right? You know that if you know to multiply by 65535, you shift it up by 16. That's just what you do. So I'm sure that I can build a 65599 out of shifts and adds. And in fact, I can, and I have done. And so I can beat the compiler here, right? I can be smarter than the compiler because what I can do is I can say that 65599 is A times 65536 plus A times 64 minus A, right? And if you do the math down the bottom, it works out. And so if I compile this, you'll see that I have beaten the compiler. And no, the compiler has beaten me. What's happened here, for those who are sort of following along, is that I have deliberately broken this multiply into shifts, adds, and subtracts. And the compiler has diligently worked out that my series of shifts, adds, and subtracts is the same as multiplying by 65599. Furthermore, it knows that it's cheaper nowadays to actually do the multiply, especially on the Haswell chipset. And so it has replaced my code with a multiply, which is awesome. It saved me from myself, right? I was making a performance regression by being clever, and the compiler went, nah, I know what you're doing, and trust me, I know more better than you. So the compiler is super smart. I was blown away when I first noticed that the compiler is able to essentially reverse engineer a multiply out of these shifts and adds. The cool thing is that it only does that when it knows it's profitable. If I actually go back to like a Pentium here, Pentium M32, so now I'm targeting the old 32-bit Pentium. You can see that it hasn't done that trick. It hasn't used the multiply because it would be more expensive. But then you have to ask yourself, why don't I just trust the compiler? Why don't I trust the compiler completely? So I'm just going to say A times 65599. And the compiler is actually better than me. It's done a better job of doing the multiply rather than building out of adds and shifts my way. It's used its own way, which is faster. But moreover, the code is readable on the left-hand side, right? There's no intent. I don't have to call this mul by 65599. Anyone can see that that's what it's doing. I don't have to have that huge apology comment underneath explaining what it's doing. The compiler does the right thing. And if we give it the right chip, then it will always do, let's do Skylake, because I can't remember. It'll always do the right thing. And so it'll do me the most performant thing. So just trust the compiler. Don't get too clever. And we'll see another example of that. And this is something that I see a lot in code. I'm trying to keep half an eye on the questions over here. If I see anyone. Oh, yes, no, people just talk about refreshing the browser and things. Okay, cool. I see this a lot in code where someone has internalized the idea that dividing is slow, which it is. And they're thinking, well, if I divide by 16, if I need to divide by 16, the best way to do that is to shift down by 4. And we're going to look at that piece of code. And, you know, we can see that indeed the compiler has moved it from one place to another, and then it says shift it back down by 4 bits. And maybe one of the reasons that you choose to do this shift down by 4 is because if you were to compare this with the code that you would write otherwise, let's just write return a divided by 16, then the compiler generates more code, right? Like this is 4 instructions rather than when I do it this way, it's just 2 or 3 instructions. So clearly my way is better. But my way, very importantly, this return a shifted down by 4 has a bug. It's not right. When you divide a negative number by, well, when you round a negative number, you have to round towards 0. That's what the C standard says. When you shift down in this way, you round towards negative infinity, and that is wrong. And I can show that by saying, you know, int a equals divide by 16, 4. So 4 divided by 16 obviously rounds to 0. I think you would agree. And we can see this is the piece of code that's going to write in the right value. Now, if I make this -4, oops, if I make this -4, suddenly the answer of -4 divided by 16 is -1. That's not the right answer. By using a divided by 16, I get the correct answer of 0. Now, I'm hearing you say, but well, I know my number isn't negative, right? So this is just junk here. The compiler is generating this junk for a value that I know to not be negative. Well, in which case, if you really know that the value is not going to be negative, tell the compiler unsigned, I'll type in a second, unsigned int a. And now suddenly the compiler is generating the same code that I had done. So it's always important to make sure that the compiler knows the information that you have in your head that maybe cause you to write these funny little tricks that aren't necessarily right. So the compiler can only do what you tell it. All right, I'm going to sort of move on pretty quickly as I'm looking at the time. This is just a neat thing that Clang and some versions of GCC can do now. So this is a simple routine that sums up all the values between 0 and x and returns that value. So like, you know, 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus ... plus x. So, you know, you probably know this is the little squiggly e sum thing. So if we look at it in GCC, you can see the code actually is generated pretty sweetly. I'm going to go through this code reasonably quickly. The first thing it says is test EDI with EDI. Remember, the first parameter that comes in is in EDI, so that's the value x. And it says if EDI is 0, is what that's doing, then jump to L4. L4 is down here. It says set EAX to 0 and return. So if the x value is 0, there's no need to loop at all. And I sort of glossed over this. I'm saying that like this XOR EAX means EAX is set to 0. That is why the XOR came up in that list of the 20 most run instructions. It turns out that exclusive ORing a register with itself, or indeed anything with itself, always gives you 0. And the encoding for this instruction is much smaller than the equivalent MOV EAX, 0 that you might otherwise expect. There are some other reasons why you want to use it too, but this is why you see it a lot. So the reason it's so common is because you very often set something to be 0. Okay, skipping back from that. So assuming that our value x was not 0, we say initialize a counter. This is the I register here. Sorry, the I variable has been put in EDX. The result is going to go in EAX, so this will be our total. And then we sit in a loop and we say, add to our total, increment our loop counter. Has our loop counter reached the x value? If not, go round to L3. Otherwise, return. We're finished, right? So it's pretty straightforward. It's pretty easy to read that piece of code. And it's hard to imagine how this could go any faster, right? There is this fewest number of instructions in this loop that you could possibly imagine. But let's see what Clang does. Let's go straight to Clang trunk. Why the heck not? Clang, if you look up and down here, has the same get out of jail for like if it's equal to 0 to start with, then the answer is 0. But there is no loop in the rest of the code. There are these two LEAs, a multiply, a shift, another LEA, and a decrement. Now that sounds more complicated to me than a loop, but there is no loop at all. What Clang has done, oh, if I could use my keyboard, is it has found the closed form solution to the sum of numbers between 0 and x, which is to say that you can do x plus 1 over 2, or what Clang's done here is a slightly more complicated version for reasons to do with rounding and the way that it discovers this. And that's really, really, really clever. Clang has taken a loop out of my code and replaced it with a single simple piece of code. So it's actually taken an order n algorithm and turned it into an order 1 algorithm, which is super clever. Okay, given again that time is pressing, I'm skipping over to some of the more juicy things that the compiler can do for you. Oh, excuse me. Quick sip of tea. So we're going to talk about vectorization. Now, vectorization is using those XMM, YMM, and ZMM registers that I talked about before, which are very, very wide. They let you pick up multiple pieces of data at once and operate on all of those pieces of data independently, but at the same time. So adding, subtracting, multiplying can happen like 8 times quicker by loading up 8 things and then just doing the add simultaneously across one register, which I meant to do a picture for this presentation and I forgot to do. So I'm going to gesture wildly at the camera instead and hope that that gets the gist across. So here is a simple piece of code. This is something you might write if you needed to get the squared sum of an array of integers. If you're doing some kind of like signal processing, you might need something like this. And I've written it as simply and straightforwardly as possible. I take a vector, a reference to a constant vector of ints, or a constant reference to a vector of ints. West const, east const, yeah, whatever. I set my counter, my result to 0. I iterate over all the v's, and I say the result is plus equal to I squared, return result. Can't get much simpler than that. So let's take a look at what comes out when we put it into the compiler. Now, I am on O2 here, which is very important for this. Without, on O2, it won't try and do the vectorization, and you'll see why I start with it this way in a second. So this is what it looks like normally. And what I've sort of trained myself to do, and now this is to get back to the poetry analogy, is I'm looking for where the loop is, because usually the place where you're going to spend all your time is in the loop. So I'm kind of just scanning down the code on the right-hand side here. I can see this JE is going to the end. That's fine. L3 is a label, and then JNE to L3. Okay, so this is the loop here. And then when I look at the loop, what I'm going to say is, how much work is it doing for each iteration of the loop? And I'm not even looking at what the instructions are. I'm just saying, okay, I'm reading a D word putter. A D word is a 32-bit value from RCX, and then I'm moving RCX4. So I'm doing 4 bytes at a time. That is to say 1 int at a time. And then I'm going to loop back round. So for each int, this is the work that I have to do. Mov, add, mul, add, compare, jump. Okay, that seems pretty reasonable. And, you know, just squinting and looking back over at the other side over here, I can see that the work here is this mul here is doing the square, the add is doing the total, and then this compare here is saying, have we reached the end? And normally I would go over how we're finding out where the beginning and the end is of the vector, but essentially the begin and the end have been read in up here as RCX and RSI. And so it's turned it into like an iterator style loop where we're just bumping a pointer from the begin until we hit the end, even though that's not how we wrote it. So that's pretty cool. So let's turn on the vectorizer. I'm just putting on an O3 here. Now, first of all, you can see that there's a ton more code that's been generated. And I'm going to sort of scroll down to show you how much code has been generated. It's like 90 lines of code. So it's a lot more. There's definitely more fluff here. And we'll talk about what that fluff is. But using my little trick, I'm just going to skim down, and look for the loop. And there it is, right? I can see there's a label, and there's a jump backwards to a label and the compare. And so now just using that trick, I'm going to say, this is one iteration of my loop. How much work is being done? Well, YMM word, I can't remember how big a YMM register is, but the clue here is that it's moving the pointer forward by 32 bytes. So that means it's doing 8 integers at a time. Isn't that cool? It's picking up 8 integers. It's then doing something with them. It's squaring them in one go, and it's adding them as it goes, and then it's comparing and going around. So now in one loop of 1, 2, 3, 4, 5, 6 instructions, and again, forgetting how long each instruction takes, so this is a bit of a dangerous thing to do, but every 6 instructions, I am doing 8 pieces of work. That's pretty clever. And then there's a whole bunch of other stuff that goes after it. So we'll look at what that whole stuff is afterwards. But yeah, the gist of it is the bit at the beginning that takes a little bit longer is it working out whether there is enough work to do 8 at a time. And then the bit of it at the end here is it handling all of the things that aren't divisible by 8 that have to be done at the end, like the stragglers that don't fit into this 8 that it can pick up as it goes. And so obviously there is a cost associated with that. And so the compiler has to do a bit of a cost benefit analysis, or guess really, to determine whether this is a profitable thing for it to do or not. And this time it's decided it is profitable. But actually, really, what's the clever thing that's going on in here, if we go, I've kind of written out longhand in the next slide, what's going on is that the compiler has broken my problem into 8 sub-problems, and it's doing them all at the same time. Not like in a threading way, but in a single instruction way. So it has made 8 subtotals, and now it's going to walk through the array 8 at a time, and then it's going to pick up each one and square it and add it to the subtotal at a time. So I've written a loop here, this for I equals 8 to 0, 0 to 8. But that's actually one instruction. Each of those steps is one instruction that picks up 8 things at a time, squares the 8 things at a time, and then adds those 8 things at a time to the 8 subtotals that I'm keeping as it's going round. Now, remember, I didn't put any subtotal stuff in my code. This has been inferred by the compiler. And then right at the very end, the compiler has to add up those subtotals. And actually, that's what most of the extra guff at the end of the loop was it adding up the subtotals. It just turns out that it's tricky to do a sideways add. You can add vertically, but not sideways so easily. But that's pretty cool. That's an amazing transformation the compiler has made of my code. And I get the benefit of the speed up without really changing my code in any way. Well, I didn't change my code at all. It just happened when I turned the loop optimizer on. I'm seeing some questions. I'll try and get to those in a second when I get to a spot where I can start. I just want to get this next bit over here. So because, you know, most of my code looks like it doesn't look out of place out of a C with classes kind of era. So I thought I'd try writing a more generic version that uses standard accumulate. And so if I go into this version, first of all, no assembly was generated, because the thing about writing generic code is that unless the compiler knows which types you're actually going to use it with, it doesn't generate anything. So I'm just going to very quickly say auto test, and it's going to take a constant vector of int and I, and it's going to say return sum squared of I. So that forces the compiler to generate that code, and it's in line the sum squared into there. We can look over here, and again, I'm not going to pay any attention to this, but like even written as a standard accumulate with begin and end and all the bits and pieces here, the loop has ended up the same. We're still doing 6 instructions for 8 pieces of work. And then the thing I was talking about before, where it adds up the subtotals, incidentally, you can see here, this is what all this stuff is for. So that's pretty cool. But of course, now I've written it as a generic algorithm, I can try other types here. And realistically speaking, if you're working with sample data and you're doing sum squared analysis, you're doing like root mean square or whatever, you're probably going to have floats here. But we're going to get to look at what happens if we change it into a float. And you can see broadly, the structure looks the same. Let's just do our check on the loop and see what's happened. So our L4 loop is here. There's our move, there's our add, there's our multiply, there's our add. Oh, and now we've got a load more instructions before we finally get down to the loop. So bottom. So something has happened here that's rather unfortunate. Now, instead of doing 8 pieces of work in 6 instructions, we've got, a whole page full of instructions for each 32 bytes worth, each eight entries. And that's very, very unfortunate. And again, if we were in a dynamic environment where we could talk to each other in a bit more way, I'd ask people for why, but why, Matt? Why would it be so silly? The problem is that trick with the subtotals that we saw it do with the integers relies on the fact that adding integers up in any order is indistinguishable. It doesn't matter if you do x plus y plus z or y plus z plus x or whatever, the answer is always the same. The compiler is only allowed to make transformations that are indistinguishable, the as-if rule, from you having written it out longhand. Unfortunately, floating point numbers are not the kind of numbers, and it's either associative or distributive, there's one of those massy terms. The order of operations is important for a floating point number. So x plus y plus z is not necessarily the same as z plus y plus x. So the compiler isn't allowed to reorder floating point operations. What that means is that it has to do this totaling as it goes. It can't keep a subtotal. It can definitely pick up 8 at a time. It can square the 8 at a time, and it can bring them into a subtotal 8 at a time. But then it has to add the subtotals up immediately. So that it's always the first one plus the second one plus the third one plus the fourth one, and so on. And that's unfortunate. It's unfortunate. Now, there is still some hope here. There are some pragmas you can use, or lazily, I'm going to turn on a switch, but you have to promise me you won't turn this switch on in production without talking to everyone you can possibly speak to. I can tell the compiler that it's okay to bend the rules with the amusingly named fun, safe math optimization. So I'm going to say F unsafe math optimizations, and they are unsafe. They change the result. If I could type as well, it would be helpful. You can turn them on for small areas of code. I've had some limited success at doing so. So your mileage may vary. Do look. But just look at how beautiful the code is that it produces in this particular case. Now, remember, the answers from this are not the same as you would have written if you'd have done it linearly one after another. But maybe if that doesn't matter to you, if you can square it with yourself and the errors that you might otherwise see, then you can do this. This is what our loop looks like now. We've actually gone down an instruction. We've got 1, 2, 3, 4, 5 instructions for every 8 pieces of work, every 8 floating point numbers. That's amazing. It just so happens there is a multiply add instruction for floating point that the compiler can use here. So it can do the squaring and the adding in one go for all 8. Bonkers. Absolutely bonkers. Love it. Again, don't turn on F unsafe math optimizations unless you're very, very sure you know what you're doing, but know that it exists. Know that also that there are some things coming down the pipeline, I believe in maybe, I don't know if 20 had them in, but there are not standard accumulate. There's another name that's a bit like accumulate, and you can tell it the parallel algorithm to use. And one of those parallel algorithms is unsequenced. And so in principle, if you tell the compiler that it can be unsequenced, then it could potentially reorder those things. I haven't seen it do that yet, but it's a possibility. Okay, I'm going to quickly check on the questions and hopefully get to those, but then we'll talk about architectural tidbits and see how we're going. Standard reduce, somebody said there. That might be the one that can take the parameters that allow you to then say it's unsequenced. But I haven't been able to get it to be as good as the unsafe optimizations. Many ways to optimize these compromises between latency and bandwidth. Can't always trust compiler. It's just best at how to deal with this. The compiler usually does a pretty good job. I've not noticed it worry too much about throughput and latency in the kind of work that I do. And I've worked in high frequency trading where latency is the thing that we care about the most. It does maybe tend a tiny bit towards throughput, but the kind of levels that it's talking about, unless you're doing a huge amount of work and doing loop carried dependencies, then the compilers is not normally more than a few cycles longer than I could like optimally move things around for. And if you've got loop carried dependencies, I think you've got different problems. The compiler isn't going to necessarily be able to get you out of that. Or I don't think that's a very good answer to your question, but just some observations. So somebody said in my example, LEA RDI plus that, LEA RDI plus something else. I don't know that that's what it said exactly. It does stall the pipeline. You're right, Alex, in your question there. You know, in terms of like the second LEA, which I believe in your example there, one of those two would be an EAX rather than an RDI. Or oh yeah, you've got it. It's an RAX. Yes, yes, it does. It doesn't stall the pipeline. It stalls that dependency chain. Now, if we had all the time in the world, and if Phil wouldn't strangle me if I went over too far, although he's told me that I'm pretty good, we could go down in a rabbit hole of like how the out of order engine inside the CPU actually works and basically looks for dependency chains of instructions. And so it's not like the other instructions after those LEA, like the RET, for example, that RET can start running even though the LEA instruction hasn't finished. Some very clever things go on to make that all possible. But yes, the second LEA has to wait for the first LEA to complete, or rather to get to the stage where its answer is ready. And the LEA is very early in the pipeline. So it usually means that there's only a 1 cycle delay between the first LEA and the second LEA, and then the result's ready on the 3rd cycle. So we can actually see that there are some modes in Compiler Explorer where you can load it into LLVM MCA, and you can see those things. In fact, I might be able to do that right now. Why wouldn't we do that? Let me go back here just to steal the view, and we're going to just go analysis. Oh, no, this is a local Compiler Explorer. I haven't got the analysis stuff loading. Sorry, I'm set up in my conference mode, so I haven't actually got the analysis view. But if you go to the main site, you can go to the analysis view. You can paste in assembly code, and then you can run it through LLVM MCA, and it'll show you what it theorizes the relative latencies are for each instruction. All right, sorry for the disappointment there, and for going off script. That'll teach me. So who amongst us has not yearned to know how many 1 bits there were set in a particular number you were given, right? This is something we do all the time. No, I always say this because I've needed to do it a few times, and whenever I've needed to do it, it's been very important. But most of the time, it's just that kind of annoying question that somebody asks you in an interview setting. Excuse me. So this is my answer to the whiteboard question. Count the number of set bits in the value A. And let me go through it in Compiler Explorer. Why not? Int count equals 0 on the left hand. Oh, in case I hadn't said earlier, the coloration in the background of Compiler Explorer tries to link the C++ code with the generated assembly. So you can see that the sort of bluey green background of int count equals 0 corresponds to the bluey green background of XOR EAX, EAX. So you can see, and as I mouse over each block, it tries to highlight the areas on the other side that correspond to wherever your mouse is. So this int count equals 0 corresponds to XOR EAX, EAX. As we've learned, that's a way of setting EAX to 0. We're about to return count at the end, so the compiler has sensibly decided to put count in the EAX register. Brilliant. And we say, while A isn't 0, we know there must be at least one bit set, right? So there's the corresponding test and jump. If it is 0, we're finished. So if there's at least one bit set, let's count it. And then there's a little tricky thing here, which is the clear the bottom set bit. And you may have seen this. If you're a games programmer, you've done this before, or you may have like played around with sites that like lead you down this line. But it's a really fun reason, right? If you've never thought to yourself, how would I clear the bottom set bit of a number? Sit down, write out a 5-bit binary number, subtract 1 from it, and the version that's subtracted from the one above, and you'll see why this works. It's kind of neat. It's a good fun thing to do when you're in a boring lecture, which hopefully this is not. I forget also you're in Britain, so you're probably drinking. I'm glad to say. I'm here in Chicago. It's lunchtime for me. Anyway, on the right-hand side, we see that there's the count plus plus. Really cleverly, the compiler has found an instruction which clears the lowest set bit. This BLSR is an instruction. And if you look at this thing here, clear something, 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 source aspirand is 0, sets carry, whatever. Okay, you know, it tells us what the instruction is doing, and it's clearing the lowest set bit. And then we're saying if it's 0, if it's not 0, there must be another bit, keep going round. So that's a pretty neat way of, and fairly close to what I wrote in terms of the actual flow of code, version for counting the number of set bits. Now, I'll be honest with you, I've picked an old version of GCC here and not Clang for a very good reason, because if we now choose Clang, I'm going to just choose Clang trunk, why not? Something amazing happens. Clang says, it's lovely what you're doing there with your loop and your counting and your bit manipulation tricks. You must be so proud of yourself for remembering that from your days as a video game programmer. But there's an instruction that just does this. Pop count says how many bits are set. And so it's recognized my loop, a whole like 8 lines of code, and replaced it with the single pop count instruction. Similarly, GCC now has learned this trick, and it will do the same thing. There's the pop count instruction. Now the eagle, so I mean, first of all, that's just amazing. It's super cool that sort of a macro level thing can be recognized as a single instruction. And then the more eagle-eyed amongst you might be recognizing that there's some other instruction in here as well, which I didn't point at. So Clang, for example, uses a conditional move, and GCC uses a XOR EAX, EAX. Both of these are workarounds for CPU bugs. I kid you not. I think if I tell it this is an Athlon, is that going to do it? Oh, no, I can't remember what the thing is to tell it it's an AMD. AMD? Is that going to work? No, all right. Never change the script. But it's an Intel errata where the population count instruction erroneously forms a dependency chain with prior instructions, even though it has no dependency on prior instructions. And so what the compiler does here is it says, hey, clear EAX. That basically ends the dependency chain. And so it works around it. Now, it wasn't a correctness issue. The pop count instruction has always worked. It always gets the right answer. It just meant that it took longer than it needed to for boring reasons. But super cool. Super cool. Who amongst us has not worked? This is more likely that you've done something like this. You know, you've had to deal with little endian and big endian. Just a real quick one here. The compiler has you covered. You know, this relatively complicated way that I've tried to make it readable to other human beings. The compiler says that's a byte swap instruction. Brilliant. And it will use a load that does the byte swap as it loads as well. If as a mov BE, if you call switch bits with a pointer, it'll work that one out too. So it's pretty clever. Obviously, you probably use hton or htonl or something like that yourself. But if you ever find yourself having to do it, the compiler will find out and use the most optimal thing for you. Again, you should probably be calling standard is space rather than your own handwritten one. But, I'm sure somewhere along the line, you've had to write something that looks a bit like this. Is it an open paren or a closed paren or whatever? Is it one of those? The compiler does a really neat trick here. It turns the set of possible truths into a 33-bit lookup table, and it encodes it in an instruction, and then it uses a shift to pick that bit. And so there's one comparison that says, is it above 32? So if it's 33 or above, then it is not in this table. Otherwise, I'm going to pick the cth bit out of this constant. And the cth bit of this constant happens to have a 1 bit wherever we want to return true, and a 0 bit whenever we want to return false. So that's super clever, right? There's no multiple branches, which is what I would expect to see in here. So there's no branch prediction problems going on there. It just picks it out. Clang does a similar thing. It has a slightly different way of doing it, but it amounts to the same thing. So compiler's got your back there. There's my sort of explanation of it there, but I'm looking at my clock now and going, oh dear. So, that's hopefully clear enough for you to get the gist of what's going on. Let's talk about function calls, because all of these are really straightforward things that half a dozen lines of code and not much else going on. And programs, generally speaking, are a lot more complicated than that. You have functions to call and all sorts of things. So let's just assume we're going to use our sum up to. You remember, this is the thing that added up the values between 0 and x. And instead of just adding up x, we're going to call a function, which I've called identity. And I'm going to tell you, dear listener, that all it does is return the value it was given. And indeed, the comment says that too. But I'm not telling the compiler that, right? It's just our secret. So if we compile this piece of code, and I'm going to compile it with Clang as well. Remember, Clang was the one that cleverly turned that whole thing into just a closed form solution. Of course, it's not a mind reader. It can't read the comment here that says, I promise you it just returns num. It doesn't know. And so it has to call the function, and it has to do a loop. As soon as it can see the body of this function, boom, we're back to our fast closed form solution. So the presence or absence of the body of this function allows the compiler to make the optimization decisions that can be quite stellar here. We've changed an order n operation into an order 1 operation here by knowing that this was just a single value. And I think if I were to do like ×2, is it smart enough to do anything? Yeah, look, it's super clever, right? I can do all these different things inside the loop, and it's still able to get rid of the loop entirely and do whatever this crazy derivation is here. I trust it that it's right. But if it doesn't know that, it has to be extremely conservative. So function calls can be barriers to optimizations. Now, a classic example of where you want to use a function call is when you might have some kind of functor-ish like object. So this is a similar thing, except that I've got instead of it being a function call, it is an operator paren on a func object. So first of all, if the compiler can see the return x, we are back in our happy world of the no loop, no work needed to be done. It can see that, right? But oftentimes the reason you might have done this is because, you want to swap it out for a different implementation somewhere else. So this is what people are talking about when they say, virtual functions are expensive. Now, in my day, gosh, I sound old, we used to argue about how expensive the indirect call was. That is, the actual call to get to the function was, like how many more cycles it was to do an indirect call versus a direct call. But the real loser is the optimization that can happen if the compiler knows what that function is going to do, or at least knows something about it. So although if we look on the right-hand side here, this call keyword pointer racks here, that is the actual indirect call, we know that if it is a func object and it's not a derived class from the func object, then it returns x. And so we could just use our closed form solution, but the compiler isn't smart enough to do that, unfortunately. So this is the bad news. This is the bad news, that Clang certainly is not yet smart enough to do anything about this particular situation. It doesn't know, of course. It can't tell that func is a real func or some derived who overrode it. But not all is lost. If we go and if I go and look at Clang, if I look at GCC, something quite clever is going on, other than my inability to talk. Just sort of skimming down for where the loop might begin. And it's kind of a bit of a higgledy-piggledy one here. There's actually two loops that kind of overlap each other. So let's start at L6, which is just where I happen to know to start looking. And also it corresponds to this sort of tan orangey background of the plus equals. What GCC is doing is it's saying, look up the object. This is where it is on the stack. Look up the V table. Sorry, this is the V table. I tell a lie. Then look up the address of the function in the V table. And this was normally where it would then just do call RDX to say, I need to go to that instruction. I don't know where it is because its user has just overridden it. I don't know what the body of this function is. But before it does that, and you can see indeed down here on line 31, it does do call RDX. Before it does that, it makes a bet. It says, do you know what? I just compiled this whole function, this whole file, and I only saw one implementation of operator paren for func. I didn't see anyone else implementing it. So why don't I just make a bet that it's probably a func : operator paren. So let's see if it is. And so it compares the address of the function it's going to jump to with the one it knows about. If it is, hooray, it jumps to L5 and it says, okay, well, increment the pointer, increment the loop counter, add in this value of X. Now, GCC, remember, is not smart enough to do that derivation, but it has not done a virtual function call here, and it has not had to push or pop anything on the stack. And in fact, the whole loop is basically going to be from L5 to L5 here. It's just going to sit in a tight loop for all those, which is not as good as it could be, but it's a heck of a lot better than if it was actually a virtual function call, which is this much longer code path here involving this indirect call. So GCC has done some kind of partial speculative devirtualization. It tries to make a guess, and that's a really cool and up-and-coming thing. I actually haven't tried this in ages. I'm going to try it on the GCC trunk. Oh, trunk. You know, it hasn't got any better than that, because in theory, it could also infer that it doesn't have to check the type every single time. You know, like it knows that the object's not changing, so it doesn't need to do this compare every time. It could actually just jump to a whole different version of the function, which says, oh, it's a func. Fine, I'll do it in a loop somewhere else, but it doesn't. So anyway, things might be coming down the line. I know Clang has been working on this for the last couple of versions. And I believe that there's been wording in the standard change to make this stuff easier to do. And I've lost my mouse pointer. There it is. All right. I think I'm done. Yes. So what conclusions can we draw from this in this last hour and 10 minutes? Sorry. The first one, hopefully, the most important one, is compilers are cleverer than we are if they have the right information. So remember, with the signed versus unsigned, sometimes you have to tell the compiler what type it is so that it can be sure of doing things. Remember the body of the function. If it could see the body of the identity function, it could make some clever inferences about how that would work, versus if it couldn't, then it just had to hedge its bets and assume the worst. Hopefully that you've realized that assembly isn't that scary. I mean, hopefully there are people still watching the stream. I haven't put everybody off. Trust your compiler is the thing to take away from this. I know I said all these airy-fairy things about poetry and whatever, but really you should trust your compiler and don't compromise readability, because you don't need to torture your code. You very often don't need to torture your code to make it performant these days. You can just write readable code, and readable code usually has a lot of clarity about what it's doing and what types are involved, and that helps the compiler. So help you yourself reading your own code, and your colleagues who are reading your code, helping you, those people, helps the compiler, and often it generates the best code. Just be aware of the limitations, things like the visibility, not being able to see into the body of other functions. So one way you can help mitigate that is to use link time optimization, link time code generation, where your entire program is linked together and the compiler is allowed to come back in again and take a look. Now all of the different parts of your code are come together and sort of say, oh, that's a trivial function call. Okay, I can inline that. So definitely look for link time optimizations. I didn't have time in this presentation to talk about aliasing, but it's something you still have to be a little bit careful of in places. That's where if you have an int star and another int star, the compiler assumes they might be pointing at the same int star, and so it has to be very defensive and careful about that. Typically, though, if you use nice, strong types that are different from each other, the compiler can say, well, this foo star can't point at this bar star, so I know that we don't need to worry about the two overlapping. So thank you for listening, everyone. Feel free to put any last-minute questions in the chat or anything. Obviously, compiler explorers at godbolt.org. As always, I'd like to shout out to the people who help me administrate and run the site. It's a village effort to get the site up and running and continue to stay up and running despite all of the various fun and games that we've had. Actually, only last night we had somebody trying to overuse the site, shall we say. The images here are all by Romain Guy, who's awesome. And, you know, go read some assembly. Thank you very much.